Hey guys, so in this video we're going to cover how to express the equilibrium constant of a reaction with respect to concentration and pressure. So remember that K can be expressed in terms of concentration, and we designate this to be Kc. It is expressed as the concentration of the products of the equilibrium raised to the respective coefficients over the concentration of the reactants at equilibrium raised to their coefficients. So we can see that if we have an equilibrium reaction of A and B forming C and D with their respective coefficients, we can express this Kc in terms of the law of mass action, where we have the concentration of C raised to its respective coefficient times the concentration of D raised to its respective coefficient over the concentration of A raised to its respective coefficient little a times the concentration of B raised to its respective coefficient little b. And remember, this is called the law of mass action. But we can also express the equilibrium constant in terms of pressure. So we designate the equilibrium constant with respect to pressure to be called Kp. Now, instead of using the concentration in the law of mass action expression, we use the partial pressures of the reactants and the products in the reaction mixture at equilibrium. Now, the Kp and Kc values of a reaction are not necessarily going to be equal, because the concentration is not the same as the partial pressure of the reactants and products in the reaction mixture. So we use the expression of Kp is equal to Kc times RT raised to the delta N to describe the relationship between the equilibrium constant in terms of concentration and pressure. So the Kp, like we've discussed, is the equilibrium constant with respect to partial pressure. Kc is the equilibrium constant with respect to concentration. Now R is going to be our ideal gas law constant, 0.08206 liters times atmospheres per mole times Kelvin. T is going to represent the temperature, and we need to have this temperature in Kelvin in order for it to cancel out with this unit right here in the ideal gas law constant. And delta N is going to be the moles of the gaseous reactants minus the moles of the gaseous products. So I think the best way to actually understand what's going on in this equation is to do a practice problem. So in this practice problem, we're supposed to calculate the Kp value for the following reaction at a certain temperature. So the reaction is N2O4 goes to 2NO2, and we're given the Kc value of 5.85 times 10 to the negative third. So if we use our expression, Kp is equal to Kc times RT raised to the delta N, we're going to be solving for this Kp value. We're given our Kc to be 5.85 times 10 to the negative third. Our R value is a constant, 0.08206 liters times atmospheres per mole times Kelvin, times the temperature, which at this point we're going to assume is 25 degrees Celsius or 298.15 Kelvin, raised to the delta N. Now the issue is we need to solve for this delta N value, and remember, delta N is going to be equal to the moles of gaseous reactant minus the moles of gaseous product. So in this chemical reaction, our delta N is going to be equal to 1 mole of our gaseous N2O4 minus 2 moles of our gaseous NO2. So our delta N value in this problem is equal to -1. So first, multiplying this R value times the T value and raising to the -1 gives us a value of 0.04087, and multiplying that times the Kc value, we get that Kp is going to be equal to 2.39 times 10 to the -4th. So let's try another example. We're asked to calculate the Kp value for the following reaction at 25 degrees Celsius. So it's H2 gas plus I2 gas is forming 2 moles of HI gas. And we're given the Kc value of 6.2 times 10 to the second. So again, using the equation, Kp is equal to Kc times RT raised to the delta N. We're going to solve for this Kp value. Now, we need to solve for the delta N value. This delta N in this case is going to be equal to the moles of the gaseous reactant. So we have 1 mole of gaseous H2 and another mole of gaseous I2. So that's going to be 2 moles of gaseous reactants minus the moles of gaseous products, where we have 2 moles of HI gas. So in this problem, our delta N is equal to 0. Alright, so our Kc value is 6.2 times 10 to the second. We know our R value, it's the ideal gas law constant, 0.0206 liters times atmospheres per mole times Kelvin, times temperature, which in this case is 25 degrees Celsius, so same as last time, 298.15 Kelvin, raised to the 0 power. Now anything raised to the 0 power is simply 1, so that means that Kp is going to be equal to 6.2 times 10 to the second. In this case, our Kp value and our Kc value are equivalent. And the reason that this is because our delta N value is equal to 0. So that means that if delta N is equal to 0, Kc equals Kp. In other words, if the moles of our gaseous products are equal to the moles of our gaseous reactants, we're going to have Kp value equal to the Kc value. So overall in this video, we learned how to express the equilibrium constant in terms of concentration and partial pressure, and how to interconvert between the two values. Now don't forget that if the number of gaseous reactant moles is equal to the number of gaseous product moles, delta N is equal to 0, and therefore Kc is equal to Kp, and you don't actually have to worry about calculating the value for Kp or Kc because they're going to be equivalent to each other.